Okay, let's take a closer look at calorimetry. One thing we can do is surround our system with water. And if the water bath is well insulated so that no heat escapes out into the outer surroundings, then any heat generated by the chemical reaction, for example, would be transferred to the water. And we can measure the heat associated by looking at the temperature change of the water. So in this example, we have a water bath with 10 kilograms of water in it. And as a result of the reaction of hydrogen and oxygen, which is pictured here, to form water, heat will be generated. And the heat will travel from the system, which is the white box, into the surroundings, causing the temperature of the surroundings to increase. If we measure that temperature increase and keep in mind the amount of water whose temperature went up, we have a way of calculating the reaction enthalpy. So, heat and temperature are not the same thing. This is an important thing to point out. You can raise the temperature of the water in, say, the Atlantic Ocean by a couple of degrees, and that can have an enormous effect on the strength of storms that are powered by pulling energy out of the water. If you were to raise, say, a pot of water by the same 2 degrees, the amount of energy associated with it would be a lot less. Because temperature is intensive, it is independent of amount, but heat is not. So it's going to take more heat to heat a lot of water by a certain amount than it's going to take to heat a small amount of water by the same amount. So, in order to relate heat and temperature, we need to know the mass of material that we're heating. And here it's important to point out that this is actually the mass of the water that surrounds the chemical reaction, calorimeter. We need also to know, obviously, the size of the temperature change, because it takes more heat to heat something by 5 degrees than it does by 3. But then the other thing we need to know is how much heat it takes to heat a given amount of material by a degree. And that's known as the specific heat capacity, or specific heat. And it's given the symbol in most texts, Cp, but I believe Silberberg uses S. In other words, if you want to heat up, let's say, a piece of metal, you'll find that it takes a lot less energy to heat that than it does the same amount of water to the same temperature. Different substances require different amounts of heat to pull off the same change. So to figure out how much heat is associated with a given change, we have the equation that now relates heat to the mass of water that's being heated, the heat capacity, and the change in temperature of the water. Cp, or S, is the amount of heat required to raise the temperature of 1 gram of the substance by 1 degree centigrade. It turns out that the specific heat of water is exactly 1 calorie per gram per degree. That's actually the definition of a calorie, or 4.184 joules per gram per degree. And it's worth saying at this point that since the size of a degree in the Kelvin scale is the same as the size of a degree in the centigrade scale, you can use either scale to calculate the change in temperature. You can't use centigrade when the process requires you to know the absolute temperature. That has to be in Kelvin. But if you're calculating a temperature difference, let's say between 25 degrees C and 0 degrees C, that would of course be 25 degrees, you get the same answer if you subtract 273 from 298. 298 being the temperature in Kelvin of a 25 degree system, and 273 of course being the temperature at 0 degrees. In either case you get 25 degrees, so whether you do it in Kelvin or centigrade doesn't matter. That's true for delta T. Again, it's not true for T. All right, so let's take an example. Suppose we have a gram of hydrogen that we burn in an open container containing 10 kilograms of water. And the water bath was originally at 25, and as a result of the reaction, it heats up to 28.42. In a previous example, I gave you the heat that a particular process generated for, I think at that point, 0.6 of a gram of carbon, And we use that to determine the enthalpy change for that reaction. Well, we have the same issue here. We want to know the heat that was generated by this gram of hydrogen. And so first we can write the balanced equation for the combustion of hydrogen, which is 2H2 gas plus O2 gas goes to 2H2O, which is a liquid. So with this balanced equation, we can relate the amount of heat to the amount of material, and then relate that back to the amount of material associated with the balanced equation, just as we did in the previous example. But first we have to determine the heat that flowed into the water. And as I said before, Q for the water is going to be the mass of the water, which is 10 kilograms or 10,000 grams, times the heat capacity of the water, 4.184 joules per gram per degree Kelvin or centigrade, and the temperature change, which as you can see is 3.42 degrees. This is of course 28.42 minus 25.00. And if we do that arithmetic, we find out that 143 kilojoules of heat were produced. If you multiply this out and then divide by 1,000 to get it into kilojoules, you wind up with 143 kilojoules. So this is the step we're adding to the process. We need to know how much heat is generated by burning a specific amount of a material. In this case, it's hydrogen. So this then represents the heat that went into the water. But it's critical to realize that Q for the reaction plus Q for the water must be equal to 0, which means Q for the reaction is going to be minus 143 kilojoules. But that was produced by 1.00 grams of hydrogen. Remember, you match up the heat with the material, with the amount of material that produced it. So, this gives us then the enthalpy change per gram of hydrogen, but in this reaction, 2 moles of hydrogen are reacted. So what we'll then have to do is first convert to moles, and that's 2.02 grams per mole. That's the molecular weight of hydrogen gas. And then finally, because this reaction represents 2 moles of hydrogen reacting, I have to take the result and multiply by 2. And when I do that, I get the result that that reaction produces 577 kilojoules per 2 moles of hydrogen, or about 4 grams. So the difference here is that you calculate the heat associated with the given process by looking at the surrounding water and multiplying the mass of the water times the heat capacity of the water times the water's temperature change. That determines the heat, and the other important thing is to realize that any heat that goes into the water must have come out of the chemical reaction, so Q reaction is equal in magnitude but opposite in sign to Q for the water.